While we wait for Carlos, today's idea is to go over chapter 2, which is understanding foundation models. Uh, Carlos will lead that discussion. And the second important thing to define today is the volunteer for next week, which is chapter 3, and it is about evaluation methodology. So, if everybody is interested in leading this discussion, feel free to say it. We can also discuss it at the end of the meeting or put it in the chat. Today, since someone else besides me is gonna lead the discussion, I will be more present in the chat than last week, because last week was a bit difficult to handle both. Yeah.
Santiago, do you think because this chapter is pretty long, do you think we'll have time to cover it all today? Or
Which one? The second or third? Second.
yeah, the second.
Um,
We should.
I, I, I don't, I don't know. Let's see. If we don't, then next week we finish. We finish it and start it. We start with the third. Yeah.
Well,
Like,
I was thinking that chapter two is more general. I mean, there's certainly a lot of details that are
yeah,
valuable. So I'm not trying to say skip over it, but I think it's probably going to have more interesting stuff later in the book too.
Yeah,
yeah,
makes sense.
I agree with
yeah.
Patrick. The evaluation methodology chapters, both evaluation chapters 3 and 4 are really going to be more pivotal. For many of
Mm-hmm.
us who finished Sebastian's book last book period.
Mm-hmm.
Chapter 2 is pretty straightforward for many of us,
Yeah,
even though it is
yeah.
long.
Mm-hmm. Yeah. But yeah, with that being said, Carlos here. So, hi, Carlos. Thanks for joining and thanks for leading today's discussion. Go ahead.
Okay, so shall I share my screen?
If you want, yeah.
It still tells me that host disabled screen sharing.
Let me see what I can do. What can I do? Uh-huh. Where could I find that? Sure. Uh, Advanced sharing options. All participants. All right, I think now it should work.
Okay, I think that I got it. So you see this beautiful quote by Mash?
Yes.
Okay. Yeah, I wanted to start with this reminder. This is a quote from one of the members of the study group that I like a lot. He says that none of us is smarter than all of us. And I feel like I have to say this even before starting with the chapter because I am not an expert in this. Sometimes, like last week, we had Santiago, who is actually a machine learning professional. I am not. I'm a software engineer, but not a machine learning professional. So I might make mistakes. So having said that, feel free to interrupt for both questions or corrections because I might make mistakes, as I said. Um, and I also want to say that I will be making a lot of there's a lot of quotes in the slides. I always mean those quotes to be attributed to Chip Huyen because I just thought that writing the name the whole time would be a little bit like too much. So what are we going to be talking is about foundation models in particular. It's not about how to build one. If there is someone here who is very interested in that, just a quick reminder that the group just finished this other book by Sebastian Rasca, which is about how to build sort of a GPT model from scratch. So there are all of the presentations, and the book is covered precisely that, how to get a PyTorch, empty PyTorch Python project and start writing all of the pieces that make the attention model and all of that. In this case, it's not about that. It's about taking a foundation model. We're going to talk about what that means, but it's about taking a model that is already there, built by other people, and creating applications on the top of it. It's basically about that. But that is more or less what the book is about. This chapter is about the things that are part of making a model that we should still consider when making an application. So the things that we're going to be talking about are things like training, what aspects of the training of a model we should take into account when building an application. Then we are going to have a part in which we actually talk about the modeling, the architecture of the model that we are using. Then post-training, in part because we are meant, if we're going to build applications, we're probably going to do some post-training, but also if we use foundation models, they are not only a model that has seen some internet data, but probably if we use models that have been told or taught how to respond to instructions, then they are models that already had a part of this post-training thing. And then we're going to talk about sampling, which is I don't know if I saw that in this book or in a talk about Chip, where she said that this is her favorite part of machine learning or AI engineering. And I can understand that. So we are going to also talk about that. To get started, training. This is like a better data, better models is like a mantra that I have heard a lot of people saying. I don't know if there is someone who we could attribute this sentence, but this is the idea that Chip tells at the beginning of the chapter when she starts talking about training data, and is that there are a lot of foundation models that have seen a lot of data from the internet. Basically, this thing that is called the common crawl or C4 or other alternatives. And those are basically snapshots of the internet. And there is everything in there. It's like she said, think about clickbait, misinformation, propaganda. I mean, it's not like a selection of those topics, but it's a snapshot of the whole internet. So those things are going to be there. And I think that the C4 is like a selection of the common crawl where some filters were applied by Google. So it's a little bit cleaner, but yet it still has a lot of these things. What means that if we take a model that has been trained on this data set, it's probably going to have all of those things in the back. Even if the model had already some training to like not show those racist biases that it may have, but at some point it might have had it. So it's important that we know about these things. And by the way, I wanted to add one slide that is not about the book, but is something more recent than the book, and is this thing by the Linux Foundation, which is called the Open Model Initiative. I think that is very relevant in this precise point of the chapter because we are talking about using models, and there is a lot of transparency around the architecture of the models, like the Python code. And then it's common to have open weights. So you have the code and you have the weights to basically use the code in your own, the model in your own. But there is not much transparency about what data sets was the model exposed to, using what techniques and all of that. So this is a project that aims to create a standard around that. And I found that it's kind of pretty interesting. It's kind of updating the open source values to open models. So just wanted to say that. And then this is what Chip was saying. Just because it's there, there are a lot of this data set is there. There is like a lot of models using it. what means all of those problems of this data set are actually in a lot of models. Some of them will be easy to spot if we are going to a model that has just had that only had a pre-training phase, which is a very, very basic foundational model. If it has had more instructional or post-training, it probably wouldn't be that obvious, but they are there. So that is basically to say a model can be bad if the data is bad, but then there is this interesting thing that there is a model. I think this is from the fee model from, I believe it's Microsoft, where what they did was to create a very, very tiny model. We're going to talk about the size of models then, but they were able to create a very, very powerful coding model by basically selecting very, very, very well the data sets that the model was exposed to. And this is these are more or less the most interesting references. The last one is the one about this model that we were talking about, which is where they describe how they took textbooks. The title is the less original ever in machine learning, but it's about that, about how they were able to make a model that perform as well as other much bigger models just by going to the dataset and making a much better dataset. And this is telling us that when we choose a model, we can make a much better model if we have access to datasets that are explicit for the task that we want to perform. But also, as we were saying, the models are good in the tasks that were in the data set or in the things that they were trained on. And that has one of the probably most important consequences is the languages, because most of the common crawl is in English. Most of the internet, I would say, is actually in English. And this has performance consequences, and it also makes the models work a lot better in English than in other languages. I think that we are leaving behind the moment in which most of the problems are making models in certain languages. A few years ago, there was a lot of people trying to create models that speak good Spanish. But now I think that most of the models do actually, like ChatGPT, etc., are not specific trying to speak Spanish, but they do that. They know how to perform well in Spanish. So they are getting better at at languages that are not English, but yet it's still a challenge to find. There is this comes from the I believe GPT-4. It's a chart about its performance in tasks that were related to, well, MMLU, I think it's coding, math, and things like that. And I found that there is something interesting, and it's that although the model works better in English, it's something that we can see is the best performing score. But that gap that we were seeing about how much language the model was able to see, at least considering the common crowd, that gap is not directly reflected here. What means if the model knows how to solve something in English and it knows Spanish, even if it didn't learn how to solve that problem in Spanish, it can benefit a little bit from what it learned how to do in English. So good to know. But something that I didn't know, and Chip says as a warning, is that in some languages, very especially when they don't use the same alphabet than English, and when the farther the language is from English, the less computationally optimal is going to be, because the tokens are going to be bigger. Normally we have a ratio of about 74%, I believe, is words to tokens. So 10 tokens might correspond to around 7 words or something like that. But if you go to other English, to certain languages that are very, very far from English, that ratio goes to a lot more tokens for the same number of words. And that means that they are less performant, even for the same problem. It's going to take a lot more memory and a lot more computation. So it's important to know that, because if you need a model to work in a certain language, you might want, actually, even if we have very multilingual models, you might want some other model or something like that. So this is where that chart came from. And then apart from this, we have also domain-specific questions, which is, well, one of them, the most typical, is coding, but there is more in datasets than that. So the thing is that, as I said before, a model is going to be good in the things that it actually studied, as we would have done. So this is very interesting. This came from a Washington Post article about what is inside the Common Crawl dataset. And it basically says that it takes the sources and it creates some categories to say that it's mostly about business and industrial thing, technologics, and etc. So one of the things that we get from here is, if the topic that you want your model to know about is not here, then you're going to have to find a data set. But if it's here, then probably you can benefit from it, because it's going to have knowledge about it already. And this is the article where that came from. So now we go to, we're going to talk a little bit about modeling, starting from the architecture. So the thing about architectures, I mean, we have to talk about the most important thing, probably the most important paper in this decade about this thing, which is the attention thing. But first, we need to understand what it was trying to solve, which is at this point, at 2014, there was this sequence-to-sequence approach for generating text, which more or less what I think that the chart explains what it was doing, which is, if you gave it an input like ABC, it was going to chop it into tokens. Let's say ABC, in ABC, each letter represents a token. So what it would do is it would take from that sentence, it would take the first thing, it would apply whatever box here, which is, let's say, the transformation. It would apply a transformation on the first token, and the result would be combined with the second token to generate the third one, and then the result of that would be combined with the next token to generate the other one. What means that basically you have to wait for each part to be processed, so you process the next one. And that means that these models had a very strong bottleneck at the input, which is what the transformer was trying to solve by basically taking the input and putting it in processing in parallel. I insist that there is a much better explanation in the Sebastian book, but basically it's about taking the input, the tokens of the input, and comparing them with itself. So you put the input as rows, the input as columns, and you create some kind of matrix where you are going to assign numbers to basically say the first word, how much is related with the second one and with the third one. So this solved a problem that is very important in translation. I believe is where it came from initially. And the problem is that languages don't sort the words in the same way. Sometimes to say something in a language, you put the verb before and the verb and the sometimes you put that after the subject or before. Sometimes two words are have a meaning that is expressible in the other language with only one word. So to create that kind of relationships, to let the model be able to be aware of those relationships, you create this thing that is called attention mechanism, and it has its good signs and its good things and its bad things. The bad thing is that, as I'm saying, you take an input that has n tokens, and to process it, you need to have in memory something that is of the size of the square of that, because you're creating the number of tokens times the number of tokens. So you're going to have a problem that grows with the square of the size of the input. But at the same time, you can process all of that in parallel, because it's going to be a matrix multiplication, and that is something that you can send to the GPU if you have it, or parallelize it somehow. So it's going to be fast, and that means that you can remove the bottleneck that you had at the input. Still, we are going to have, as Chip says, a bottleneck on the output, because this is all a process that at the end there are going to be many layers like this, because you generate a token and then you put the generated token, you append it, and you do the same thing again with the whole sentence. So you still have a bottleneck in the output, but we have solved one of the issues, and it's much more performant than the sequence to sequence that we had before. And I took the freedom to add here one of the slides from the book, as we did this when we read Sebastian's book. And I just want to show that the part here on the bottom, that function that says def forward, basically everything is in there. The rest you can read it or whatever, but basically all of the thing of the attention mechanism is in there, which is what corresponds to the function that is written there. That it's not super impossible to understand. It's kind of although it sounds a little bit abstract, but it's basically it's a function that has an input, in this which is of the type tensor, and it will return also a tensor. And what we are doing there is we have these things that are called keys, queries, and values. I'm just going to pass very quick on this, but basically you have three linear matrices, which is three groups of parameters that the model is going to be able to learn. It's going to assign some numbers, some random numbers initially, and then it's going to perform these operations and do the whole machine learning loop, where it's going to attempt to do a solution. Then it's going to compare with whatever cost function is associated with the model, and then it's going to update those parameters with the correction that comes from whatever input and output pair we gave it. And the thing about this, I just wanted to add one thing at the end, which is there are a lot of linear transformations involved in the code that I was showing. I found that this there is. I'm going to show you the link to this. This comes from a video that explains basically what are keys, queries, and values, just in case someone wants like an introduction. But it's basically telling us the reason why we need to add those learnable parameters to the process. And one of the things that here is showing is that attention mechanism. One of the things that it helps us doing is take a concept, like in this case, the example is about the word apple, that can have different meanings. Whether you're using it in a technological context to refer to the company, or in a kitchen or a food-related context where you are talking about the fruit. So what this is telling us is that you might have an initial space embedding like the first one, like the squared one. In this case, that might work if you do the products between one of the spaces and one of the embedding in the other one, you might get something that helps you differentiate, because after the first product, which would be like dot product, you're already going to have the word either closer to technology or either closer to fruit, let's say. But if the embedding that we have was somehow closer to the one in the middle, then applying the operation would not be as effective, because they are displaced with the same logic. They are displaced, the word is displaced to either technology or Apple, but if the space was something like that, it wouldn't help much. So that's why a linear transformation helps, because the system might learn that if you take this kind of the last transformation before making those dot products, then the result would be bigger. The difference would be bigger than when you apply the transformation. So it's interesting to take that into account. And this is what I was saying.
I have a question.
Yeah.
So in Chip's book, when he talks about the different vectors, the query key and value vectors, there's an intuition about each of them. The first one is thinking about the person is looking at information to create a summary for the query vector, and the key vector, it's a page in the book. That's how he describes it. And the value vector is it's like the page's content is what was used to describe it. I wasn't understanding these intuitions as it relates to what you were just discussing. The dot product and its position in this embedding space. I wasn't connecting these intuitions with how it's actually working. I'm not sure why I'm not able to, but it just wasn't clicking for me. And I was wondering maybe you could address that a little bit more.
Yeah, to me, if I go back to the code, I mean, I would just tell you a glimpse of what I understood, but then if someone else can give us a little bit more insight on this, it could be also good for me. But if you look at the code here, keys and queries are almost the same thing, are a way to put the input against itself and compare the input against itself. And then this happens normally, I mean, this is one block, attention block. Normally in a GPT, you have many of them. So you're going to have it initially on the input, but that is going to give you back an enriched embedding, which is, as I said, more or less what I was saying before. You would have, if we were talking about technology, you would no longer have the initial Apple embedding, but something that is slightly towards technology. And it would have, again, this operation. So you would theoretically go every step a little bit closer to whatever the context is pulling it. But initially, if you look at this is both the key and the query have the exact same treatment. You get X as an input, and they are just parameters, and then you multiply one with the other. So I think this is more or less they have more or less their same role, at least the way I understand it. But if anyone else can give us a little bit more.
Yeah, yeah. In my opinion, when I was reading Chip's book and her analogy on it, uh, it also didn't click too much for me. Like I understand like the explanation of key, query, and value. I got it. Like I got a better intuition about them from Sebastian's book than this simplified version in this specific chapter. I think it was like, okay, why why would query be? I don't remember the intuition that Chip gave, but why one be the book, the other the page, and the other uh, the specific version? For me, I I was like, wait, I didn't get this, but uh, I'll stay with the Sebastian's explanation. I didn't try to like actually get it.
Yeah. Anyway, it's quite abstract thing, and I still have my head. Even if I already called it with Sebastian, I called it an attention, and I made some simplified cases in which I could see what was happening. But still, it's like all of the concepts are pretty complex because there is not like a direct intention when you write machine learning code. You add linear transformation in there, but you don't say what that linear transformation is. It's going to be decided on training time when all of that back propagation happens. So it's quite difficult to actually put names to what everything is. But that's
Mm-hmm.
what I can say. Yeah.
Mm-hmm. And when Michael is saying in the chat that he says that he always struggled with some of these high level intuitive explanations, same for me happens usually when you go too deep in that level. That okay, I just understand it. It's we have two matrices that are their weights are tuned by backpropagation, and actually the values this course is actually like the multiplication between those are you are like okay, happy and getting it. But when you then abstract that to a higher level explanation, it's like, okay, no, it's just matrix multiplication. And I think there's like a next level. So there are like three levels of understanding that I generally see. It's like, okay, you have the high level explanation, then middle part, um, okay, I understand everything as matrix multiplications. And then last part of you already understand mostly everything, you go back to high level explanation because now you see it in another way. So you can picture this mean that is like the midwit mean that is like a standard a normal function, normal distribution, and you have like the first part that is like the noob that doesn't know, and it's like the high level explanation. Then the middle part where we could say we are that is like okay, I understand that this actually just matrix multiplication. I can code it whatever, and then it's this like other part that says the same thing as the noob, but now uh, with a more reflective and perhaps better understanding. And I feel that's what Chip's doing with her analogy. It might have a different background that was perhaps not very clearly explained in simple words, but yeah, just wanted to
Yeah.
mention.
Yeah, I also have the feeling that I will have to go back and forth a lot of times. What means I have to go back to the code again, code it again, even if I already did it, and then try to debug, and then go to stop that and go to books like Chip's book again and see the analogy and try to see if this time I get it better. But I don't understand 100%, and but yeah, yeah. So this at the bottom, this was the link at the bottom is from the video that I was talking about, which explains more or less these concepts, and at least is the video where I understood why we needed linear transformations, which is something that I didn't understand quite well after Sebastian's book. And then Chip starts talking about other architectures. I found this, she says that developing a new architecture that outperforms transformers is not easy. And she was talking about a presentation by Ilya, which I found is pretty interesting. Although it's again, it's a video. I added a minute just in case you want to go to the exact part when he says that. But he's talking about different ways of teaching an LLM, and he talks at a certain moment about moving from supervised training to what's the theory behind training something like we train now GPTs, which is basically unsupervised on the whole internet. And he basically explained a little bit about something that we are going to see when we talk about model size, which is scaling laws. And he says something that is something like, if you are able to create a model now that you're even smarter than the transformer model and you achieve to make something better, then you have one challenge yet, which is the current model might be able to model your model, which is better than the current model. Because I believe that this has to do something with the fact that GPTs with where they have all of these models, all of these attention mechanisms in series and all of that. I believe that that is kind of, in a way, and you can understand that as a model that can auto-program itself, and it has a big level of generality. So it can create very complex models, what means that even if you make something better, it could learn that. So that's why I believe that she was saying, because when she said that, she referred to this video by Ilya. So I believe that this is kind of the key. This is called the simulation principle or something like that. But that's basically the way she starts talking about other models, other architectures, which we should kind of be aware of. I didn't know this one, and by the way, I don't know how to pronounce RWKV. If you go to the website, the first thing that it tells you is how you pronounce it, and I don't understand it either, so I'm not going to say that. But it's another model. It tries to tackle the way the problem of context length, because the GPTs and the attention the models that are based on attention blocks, they have this thing that you're going to have a maximum size of a maximum context length, because basically you have these parameters that are those linear matrices, and you're going to train matrices of a given size. And if you train 1000 or 2048 times 2048 or whatever size you gave them, well, that was probably a very big number. But if you gave a given number, then something bigger is just outside. So you would have to either chunk the input to feed it to the model or something like that. So these models apparently are trying to tackle that problem. And I found interesting that they have this thing called the link behind below, sorry, which is a version. I couldn't make it run very well, but it's interesting that they offer a model that is is less than a billion parameters, but it has the characteristic that it's just around 300 megabytes or something like that. And you can open a web browser, it will download the model, and using web GPU, the intelligence would run on the client. I just found that it's the first time that I find something like that. It's interesting. I'm just saying that. And then there are this is what we were saying. This is one of the issues, and other architectures that are mentioned in the book are basically, as the model that we talk about, are also trying to tackle the same problem, which is we all want to have infinite infinite context length models, because we want to take a model that is someone smart, and we want to feed it with a lot of information, our books, our websites, our database, and we want it to process all of it and understand parts or information that might be hidden in all of it. So that is one of the problems that probably the next generation models will solve. And one of the approaches that seems to be very interesting is what are called SSMs, which is space state models, which is kind of, they take a little bit of the advantages of more or less of the philosophy behind attention models, although they don't, they approach things in a different way. But apparently, one of the things is that they are more efficient because they don't have these matrices of the attention, which means they don't have these quadratic operations where you have to sort of multiply the input time itself. But apparently, something that happens to them is that even if they work well in very big context, they normally cannot give you the warrant you cannot be sure that with big text they are gonna perform well on all of the parts of the text. So still they have challenges. But they have this thing that they can still retain memory over long text, because basically what they do is they process chunks or something like that, and they create a model, a space model of what they read, and then they keep doing it and passing that sort of sequentially. So I have not called it any model like this, so I don't have any code to show, or I don't know about the specifics. But apparently the idea is that they don't have this limitation of being restricted to context, to fixed context length, which I think is probably what we're going to be. Actually, I've seen Sam Altman saying that this is one of the problems that they want to solve in the next generations. So I actually asked ChatGPT. This is a bit of an obvious question, but I asked it if they were using SSM, and they told me that they are not using them, but there is a strong evidence that they are researching on them. And apparently it said they might use it in GPT-5, which probably mean if it's called GPT-5, I guess it means it's going to be something like Jamba, which is a mixture between space state models and GPT and transformers. Because if they switch to SSM, it wouldn't make sense to call it GPT on the end. But this is basically that. I was also mentioning I mentioned this already, which is there are intermediate models which are using both of SSM and transformers. So I'm not sure how they do that, but apparently they can both not have limits. But I guess what they did is that those boxes that they have for the part of sequential processing, in those parts, I guess they still use transformers. So that's interesting to know. And apart of that, we still have to talk about model size. As I mentioned before, Ilya's talk mentioned something about the scaling laws, and it's basically about the thing is that what attention mechanism made is it helped these models processing a lot more information, because basically we can process faster, so that's very related. But there are things also that we have to take into account. I mean, on one side, bigger models are better. They can process more information. They know more stuff. But also, on the other hand, as time passes, if we put the focus in something like Llama, on the models of Llama, we can see that the 8 billion parameter of Llama 3 outperforms the 70 billion parameters of Llama 2, and they were separated by something like 1 year, more or less. So it's interesting also that with time, even the tinier models get better. That's also something interesting. I found a very interesting way also is to make this computation. I never knew that it was that simple to estimate the size of a model, but as well, it depends on what type of parameters they have. But if they have a 2-byte or a 16-bit per parameter, which is the float type that you use. It would be the standard float 16 that PyTorch offers, or almost any programming language. In that case, you just take the number of parameters, you multiply by 2 because it's per byte, and you get the size, an estimate of the size. So a 7 billion parameter would take, as an estimate, 14 gigabytes of memory. And that has exceptions, like especially if they use something like sparsity. Apparently, sparsity is something that mixture of experts use a lot, like Mistral, where you have a model that is basically 8 models at the same time, roughly speaking. And one of the things that apparently happens, I didn't know about this, is that they share a lot of parameters, but also they use this technique called sparsity, which what it does is it takes many parameters that are close to zero, and it basically takes them to zero. I believe that I'm being very, very vague here on how they do that. But what's interesting is that those parameters are not taken into account. Like when you're going to multiply, if you have two vectors and you know that one of them has a lot of zeros, you don't even need to read those part of the second vector, because you know that the multiplication of that part is going to be zero, so it's not going to add up anything. And that basically means that they perform better than what they would perform if they did not have those zeros. So they take less space in memory and they compute. It means that if you want to make the estimate that I was showing before for the 8 times 7 billion of Mistral, you probably would overestimate, because as they have zeros, it's not just multiplying this by 8, but a little bit less than that. So that's interesting also to know. And then there is this thing, like if you have a bigger model, one of the things that you're going to need is a bigger data set to train. Because obviously you want to more or less, if the idea is that if you performed on a model a certain number of operations to get some number of parameters trained, then if you have a bigger model, you're going to have to do the same, and you're going to need more data for that. So as a reference, Llama 3 was training 15 trillion tokens. I might make mistakes also when I talk about these things, because when I talk in English, I use the American naming for billions and trillions, which is quite weird to me, because we use a different standard for that. But anyway, I found that these numbers are quite mind-blowing, because when you try to see how many operations were performed to train something like GPT-3, which is not even one of the biggest models as of today, the number of operations this is counting floating point operations, which means let's take one of those numbers that I was talking about, one of those floating numbers, and multiply by another. That's one floating operation. So to train GPT-3, the estimate is that you need to perform 3 times 10 to the 23. This is on the order of Avogadro's number, so it's a quite big number. And the estimate is about $4 million if you consider things like you are going to have already everything in place, and you only need computing time to just run the process, because you have everything in place already. But I believe that the consequence here is we are definitely probably going to, in case we want to have a specific model for us, we are going to start working on a pre-trained model, because unless you have $4 million, you're probably going to prefer to take something that has already been trained and just run post-training, which is much more efficient and economic. Then there is this thing that are the chinchilla scaling laws. which I didn't understand quite well. I believe that is something like if you, I mean, we have said things that gave us the impression that you just train more, have a bigger data set, and everything is going to be better. But apparently there are things that started appearing, like even the I believe that in the book there was said something like even the model starts complaining that it was not want to be turned off, and some things that were fixed during the training, like um, hallucinations or things like that, it appear again when you keep making the model bigger. So there is this thing called chinchilla scaling laws that helps finding some of a balance. So it's once you have a model, it tells you that for that model you don't want you don't want to train forever on any dataset size, but if you have a certain model, a certain number of parameters, you probably want to stop at a certain point. It gives you some sort of sweet spot. So good to know also. And this is an estimate of that. Apparently, for compute optimal training, if you have the number of tokens, if you have the number of parameters of your model, you multiply it by 20, and that's more or less the size of the data set that you're going to need to train your model. And now this talking about sizes and about size of data sets and about how much computation it's needed, there are two bottlenecks. One of them is data, and the other one electricity. Regarding data, it's interesting that there are many things here regarding data. One of them is apparently if we still learn how to make these models and these processes of training occur faster, then there is a point where we are not going to be able to have that much new data generated, because if it grows faster than the internet, that number, then there is a moment where we are going to have to find data in a different place, maybe generated synthetically or something else. But there is also the thing that many people started saying, hey, I don't want my data in your model. And apparently almost half of the common crawl is now restricted because of that. So there is that problem. That's why data is one of the problems. And the other one, which I found is even more important because of like we have limited physical resources and they affect the planet, is electricity consumption. This is as the models are growing, then the necessities of computation are growing, and apparently the solutions are just we need more electricity, which is also a big concern. And now we get to the part, so we have talked about training data, we have talked about modeling and model architecture, and now we're going to talk a little bit about about what aspects of the models we should take into account when we are talking about the post-training. So basically there are two things that we want to solve when we do post-training. One of them is that when you do only pre-training, that exposing the model to something like the common crawl, it will learn a lot about the language. It will learn a lot about what word should came after another word and syntax rules and all of that. And also it will learn a lot of facts, but it will not learn how to have a conversation. If you have ever used a model that is not it does not have instruction tuning, but only like let's say a base model, normally you set something, you start a sentence and it gives you back something that it might be correct syntactically, but it might not be answering your question. It might just continue. You make a question and it continues like it was a dialogue in a book or something like that. So learn how to respond like you are in a dialogue is one of the first things that we try to address when we do post-training. And the other one is, as we said, there is a lot of wrong information, biases, and things that we don't actually want the model to rely on. So those fixes are also part of the post-training. And this is an analogy that Chip made. Is like pre-training is like acquiring knowledge, but then post-training is learning how to practice it, which is, I think it's a nice analogy. So regarding this post-training, well, we already said that it requires significantly fewer resources than the training, because it's the big part has already been done. Now it's about that's why it's called fine tuning. And we're going to start with the first type of fine tuning, which is the supervised. And this is about basically taking high quality instruction based data. The fine tuning data sets are normally instruction and the way you are expected to answer the instruction. And I liked a lot a way that Chip made to explain this, which is the pre-training is something like token level training. We want you to know when you have a word, what's the next one, something like that. And in this case, it's answer level. It's like, I want you to know that when you're asked something like, please make a summary of this text, and I gave you a text, then what I want is not you to answer with another question, even if it's syntactically correct. But what I want you to do is to actually make a summary. So it's more understanding the context and the part that you play in the conversation. And regarding preference fine-tuning, this is another part of the fine-tuning, but in this case, it's about telling the model basically how we want it to do the things. It's more like a flavor thing. Also, as there is a lot of people who is in following this book, but was not in the following Sebastian's book. After the last chapter, Michael, which is one of the group members of the study group, made a presentation about one of these things, which is it was an extra part of the book about how you can do this thing called preference optimization, which is quite interesting. And also Santiago has a post. I think it was a post or no, a video in YouTube about reinforced learning. So these are techniques that are more about telling it. The direct preference optimization example that Michael told us was about basically making the model more polite or less. And it's about, you have to kind of tweak a little bit the model, but it's about giving it different options and making it learn how to prefer the one that was most in the line that you wanted. So it's, once we have already the model, this post-training is basically about making something that answers and answers in the way that you want it to answer. So now we get to the Chip's favorite part of the book, which is sampling. And sampling is about basically generating something that goes a little bit beyond the next token. The models, when we talk about in particular GPTs, we typically have a last layer that is called logits, which is, it contains the size of the vocabulary. Like in the case that we did in the last book, was we were using the values of the open weights of GPT-2. And it was trained in 50,000 tokens in a vocabulary of a size of 50,000 tokens, what means that the last layer was a vector, just one dimension with 50,000 rows. And each of them has a number that what it does is when you give it an input, it's going to calculate the values for all of those numbers. What means even if you then choose one of them and interpret that as a probability and say, I'm going to take the one with the highest value, which is the most basic way to generate an output, that would be making your model work with the next token, predicting the next token. But the model has learned more than that, much more than that. It knows how to order all of the tokens in the vocabulary, so it can give you either the most likely token, or you can apply more policies because you have that information, so you can do more flexible choices than that. The first one typical is to apply a softmax, which is this function at the end. And basically what it does is you have logits. Logits are numbers. They don't necessarily add up to one or something like that. So they are just, but they are related with probabilities in the sense that if you do this thing, which is a normalization, it makes the whole vector of that last layer in the model, it makes it add up to one. So it makes it be interpretable as a probability for each of the token to be the next one. And what's interesting about this is that you can use that, and then rather than taking the most likely token, you can get those probabilities. And if you have, let's say that it's a tiny model of 2 or 3 words, if you have 0.75 in one and 0.25 on the other one, then you can apply the softmax and interpret it as a probability and return 75% of the times the token that had 0.75, and the 25 restant part of the times, remaining part of the times, the other token. That's kind of a very straightforward approach. Just take the layer, interpret it as probabilities. The tokens that are very unlikely are going to occur in very few occasions, but it still might not be what you want. You might want to avoid them at all costs, because you don't want to use, you know that the tokens that have very, very tiny values in the last layer are very, very unlikely to generate good quality responses. So another thing that we can do is start talking about different sampling strategies. There's a lot of them. We're going to talk about 3 or 4 different techniques, but it's always about making from something that's more or less predictable, which would be this thing called greedy sampling, which I already talked about, which is taking the most likely token. Or the probabilistic one, which is applying the softmax and just applying a normal distribution following that as if it was a probabilistic rule. But we can go a little bit further and do some strategies. The most common one is when we do the softmax, we add an extra parameter, which is, we're going to call it temperature. And it's basically another way of normalizing. It's also the result is always going to be the sum of the logits. If you apply this softmax with temperature, it also is going to add up to 1. So it's still something that you can apply as a probability. But the difference is that if you increase the temperature, then the tinier values are going to become a little bit higher. And if you decrease it, you're going to make the most likely token even be farther away from the other tokens. Which, by the way, in the book, I believe, I might be wrong, but I believe that there is a tiny misinterpretation of this, because what it should say is that for t lower than 1, you're basically sharpening the possibilities. What means if you apply a value like 0.5 as it's written in the book, what you're going to do is the most likely token is going to be even more likely. So, and the less likely ones are going to be less likely. You want to increase the temperature, and let me go back to the formula. If you apply 1, you are getting the same thing as if there was no temperature. So you just using the probabilities of the model without temperature. 1 is the reference value, and higher values that are higher than 1 are the ones that are going to give you more creativity, in the sense that are going to take the things that were less likely and you're going to basically modify those probabilities so they are a little bit closer to the highest probability. And that's something that it's interesting because it gives you more a wider topic of a wider number of different results. You can, if you apply this, you might also combined with the next things that we want to talk about now, you may get different answers each time, which is where I think sampling is interesting. And to do so, one of the approaches is to choose a number of instead of taking the 50,000 in the case of GPT-2, instead of taking all of those numbers, you can try to make this more computably efficient, because this is something that for each token you're going to do that, because the entire GPT model is going to generate a token and then it's going to append it to what was the input, and the whole model is going to run again. So the last layer is going to be executed every time, and it has this size of 50,000 in the case that your vocabulary size is 50,000. So you're going to be running that function, that normalization, this softmax, you're going to be running it on 50,000 elements, which in many cases is not what you want. If you somehow choose a number, like in this case, it tells us to choose a number between 50 and 500. This means you can order those values from the logits and say, I'm only interested in the most likely ones, let's say the 50 most likely ones. And then I'm going to only normalize those 50 ones or those K ones. That's one of the approaches. The limitation that this has is that sometimes you have a word in sentences where you want that the number of options in this case is like is a constant that you set, and if you say 50, then it's always going to be 50. But sometimes you want that to be like that, and sometimes you want to be more flexible. So one possibility to make this a little bit more flexible is to choose a top P. Top P stands for probability. In this case, what you do is you say, okay, I don't know how many of the tokens you're going to consider, but I want them to add up to 90%. So that means if the sentence with the context is something like the capital of France is, then it's very, very likely that Paris has already something like 0.9 because it's probably the next word. So in that case, the top P is going to give us probably one or too many other options. It might be something like Paris is a city. That is probably not going to be 0.9, but that is going to be one of the few options. But if the sentence is something like my favorite city is, then all of the cities, all of the names of cities are going to have a tiny value because any of them can be, and there is a lot of cities. So in that case, a top P of the same value is going to give us a choice between a much bigger number of values. So that's the difference between top P and top K. And then there is also another approach, which is to try to filter by minimum. If I understood, I never used this one, but if I understood properly, what it says is I don't want values with less than a given minimum probability. So you basically just remove things that you consider that are kind of almost zero probability. So you make, it's another technique for dynamic sampling. And now we get to test time compute. I was surprised to find this in the book because now we are talking a lot about test time compute, because test time is the kind of technique that is used in reasoning systems, in reasoning models. And I believe that this is something from even after the book was written, if I'm not wrong. But anyway, it's about if we is something that happens when the answer is already being generated, and the idea is to try to not apply selection on tokens, but apply selection on answers, on entire answers. So the approaches are diverse. Some of them are about generating many answers and displaying them to the user, which I have seen, by the way, I believe in ChatGPT sometimes. I have made one question and I have had two answers, which is interesting, and the system tells me which one do you prefer. So that's one of the approaches, which is just asking the user to choose the one that they prefer, or apply another selection method with another. Chip also talks about using an AI, another model, to just have the answers and decide only what of those answers is the best one. Then one of my favorite topics is structured outputs, because um, many times we want to use an LLM to do something that we're going to integrate with some other platform. Actually, some tasks are directly like text to SQL. Is sometimes you directly want the model to generate something that is not English, even if you are asking in English. Like this thing, I have a database and I want you to tell me how to get the last orders that were completed by the best clients that I have, or something like that. So the answer must be an SQL query, valid SQL query. But sometimes it's not that obvious. Sometimes it's just that the model is going to be in a pipeline where there are more steps. Like maybe this is going to trigger, it's a chatbot that is going to trigger a reservation in our database. So our database is not given by an LLM. It needs a call to an API. So you need somehow the LLM to be able to generate that call. That is very closely related to function calling, which I believe is almost kind of the same thing as structured outputs. And the thing is that if you want to have the model doing that, there are several strategies. The easiest one is just prompt it. I mean, I've done it a million times. You just tell it, give me the answer in a JSON valid format. And most models of today are able to somehow give you formats. If the format is pretty standard, like JSON or something like that, they already know how to do that, and sometimes it would work. And I find that this is quite interesting because it also helps testing. I mean, if you want to see if a model knows the capitals of countries, you can ask it, but it's probably gonna answer with sentences. So you are gonna have to either apply regex to see if the name of the correct output is there or something like that. But another way is you can ask it and tell it, please answer with just a JSON that contains answer with the value, the name of the capital. So just prompting sometimes works, and it can let you easily test the system. But that has limitations. Many times it will generate data that is almost correct, but not without a closing tag or something like that. So if the case is easy, you can post-process the output. I have never done that. I mean, I was surprised to find this as one of the suggested outputs, but I guess I guess it's something that pops out a lot because it's suggested as one of the techniques, which is sometimes you get an answer that is almost structured but not fully. So a tiny post-processing might help, and you might still not have to discard the answer, which is a shame. But then there are other tools that are a little bit more, how do you say, a little bit more elaborate, like trying to constrain the output of the model. This works because many times when we are seeking for a structured output, what the structure output is precisely something constrained. And I took the liberty of taking one of the screenshots from the JSON specification. Is basically that. It's basically telling you what is a valid JSON object. Well, it's something that starts with a bracket, then it has either a white space or a string, blah blah blah. So what these techniques, constraint sampling, do is basically trying to force that. And one easy to think about is just ask it, but via prompt, generate a valid JSON, and then try to parse whatever they gave you as a JSON. If it's not valid, then the answer is not a valid JSON. Not super efficient. So that's why there is this suggestion that Chip is kind of making, which is if you need something better than that, you might want to actually take a model, pre-trained model, and teach it how to actually generate in the first place something that is actually a good answer, because it's going to be more efficient. It's not going to be a call to a model that I take the answer and parse it, and if it's good, I pass it. It's going to be a call to a model that actually generates something valid. And she proposes some sort of way to do that with the classifier layer. I don't fully understand this. If someone wants to tell us something, I guess it's basically about rather than having tokens of the full English vocabulary or something like that, I guess you will restrict that somehow to get something that is valid in the space of outputs that you want, JSON or whatever. But I can understand that if you fine tune something, you can force the model to generate the outputs that actually are valid in your space, in the space that you wanted to generate. And that's almost all of it. Then there is just a little bit of talk about the probabilistic nature of AI. We have seen that sampling is basically the strategies that we take to either generate richer outputs or just to generate outputs that are closer to what the model has learned. But in any case, even if we took the decision to always show the output without temperature, and we wanted to output the most likely token, still there is a lot of probabilistic things in there, because in the first place we chose some data set to show to the model. So, and we are we're making it model in something that is close to making probabilities of what the next token is going to be, even if then we don't take it crazy and let it shows different values each time. So at the end, is basically the models are going to be either more or less probabilistic, but they are going to be probabilistic in the end, at least with the techniques that we are using as of today. And that means two things, basically. One, is going to cause inconsistencies, and it's going to cause hallucinations. Inconsistencies means that if we change a little bit the input, we might get very different outputs rather than outputs that are just slightly different. And that's more or less yeah, I was saying here that even the selection of the data set contains some randomness. But this is what I was trying to say, that is there is this concept of what the model of a model being robust. And the thing is that if a model is not robust, then two users might be trying to get the same output, but they are going to use different ways of asking for it. And what we would like is the model to actually perform in the same way, not very differently, depending on whether someone wrote the input in uppercase or lowercase or something like that. Those differences, we don't want it to affect the output in general, unless it is about that. So to mitigate that, there are some techniques. One of them catching the answers, and another one is tweaking the parameters that we have been talking about. But still, I believe that these two problems that we are talking here are just problems that we have to mitigate in all cases. We are never going to be able to, with these models, 100% get rid of them. We are going to have inconsistencies, and we are going to have also hallucinations because of the way they are built. And I believe that this is now the last slide, if I'm not wrong. No, there's another one, but this is almost the last slide. This is to say, try to talk about why hallucinations exist, and apparently there are two main hypotheses. The first one is that, as we saw, the GPT models, they work with their own input. I mean, they start with the input of the user. They generate one more token, and now they use that as the input and feed again the loop from the beginning. And that token that it generated is appended as if it was part of the input. The model does not know that it was not. So that is very useful for generative purposes, because you start a sentence and it completes and it goes on with whatever it said. So it's going to generate something that is consistent. But it does generate this problem that is called snowball hallucination, which is if it starts saying something wrong, then as it came as part of the input, it's going to assume that it's a fact. So that is one of the reasons for hallucination, or at least one of the hypotheses. And the other one is that sometimes we are using supervised fine tuning, which is we are telling the model, well, to this problem, you should give this answer. But if we are not telling it, if we are not including in the solution how do we say, the reason why we took that as the answer, if we are only giving it the answer, then we are maybe training it to hallucinate, because we are not only programming the machine for the input that we are giving it right now, but it's gonna try to do the same with a similar input. And if the similar input, if I tell it, tell me more about this paper, and I gave it the name of a paper that does not exist, maybe it's going to try to mimic the answers that it has seen before in trainings where we were talking about papers that actually did exist. So it's it's interesting that if we do not take these things into account, we might be actually training the model to hallucinate. And then there are some solutions. One of them is to ask the model to include sources. So that is not a solution that does not prevent hallucinations, but it makes them easier to spot, because like when you go to Perplexity and you ask something, you get some links. You can almost ignore the text or just give a quick read and then go to the sources, and you're going to see if it was actually hallucinating or not. But at the same time, it seems like asking them to include the sources actually does reduce a little bit the hallucinations. And also a technique that's a little bit magic, but it also works, is telling the model to actually be honest. So if you don't know the answer, don't say anything, or just say I don't know. And apparently this actually does work in many cases. And the reason why it seems to work is because you are basically letting the model stop, so it does not have to generate, and it does not get itself in these snowball problems, because it actually, if very soon it knows that it does not have to say anything and it's allowed to say I don't know, then it basically does not get in the first place. So that's basically it for the chapter of today.
Awesome. Nice. Thanks for it was a great recap. I also learned a lot from it. I feel this chapter was kind of a nice high level overview of of a summary of all Sebastian's book, basically. Uh, yeah, thanks, Carlos, for taking the lead on this. Anybody has any question? No?
Excellent preparation.
Yeah, it's pretty good.
Uh, like, could you summarize the post-training techniques that like you found useful and like Chip has alluded to in the book once again, so I kind of like missed up upon it.
Sorry, your question is about the post-training techniques related with
Yes. Yeah.
but yeah, yeah, there are like there are many situations where post training is kind of useful. I heard, I believe that is in an interview that she had recently in YouTube. She said something like pre-training is about facts and post-training is about the shape or about the form. So it's more or less. I found that this is kind of interesting. So the techniques are basically you start approaching rather than the each of the tokens or what's the structure of the language or the facts. You now go and decide what are you going to do. What's the application that you're going to do with the model? You're going to do either a chatbot or you're going to do a something that generates queries against a database or something like that. So that's when post-training, I believe, that comes into place. And the techniques are a lot of them. Sometimes they involve tweaking the model a little bit. Like if you want to do something to classify spam, then you probably want to change the last layer. And instead of having information about the next token, you want to have just something telling you if something is a spam or not and what's the confidence of that answer or something like that. So that's what I
Yeah,
can say.
and plus for the instruction tuning techniques, various reinforcement learning approaches that have cropped up over the past year. So, like I was thinking, like maybe we can have separate session regarding that since like uh if we want to have a base model of suppose you're training a 1.5 or 2 billion model from scratch and you're using common crawls and like you filter the data, you do a series of pre-training based on a particular mixture of experts that's like very much on the like market today with the deep speak and various multi-head related attention mechanisms that have come into place and you like to uh, you complete the training, you go into the post-training phase with the that. So yeah, I was wondering, since like the last cohort that we did, they with Sebastian book, he didn't include any post-training techniques. So like, yeah, we can have a separate session after, of course, this book is over. So like, yeah, that was my kind of a thinking regarding that.
Mhm.
Yeah, definitely.
Yeah,
I mean,
go ahead.
yeah, I was just going to say that definitely. I mean, that's the point where we are right now, which is we have models and we want to do things about with them. And the thing is, I think that something that would be very appreciated is if, as there is people with actual experience here, fine tuning and all of that, if they could at least point us in good directions, because one of the difficulties here is that sometimes these processes, even if they don't take as long as a pre-training or they are not as expensive, but still these processes tend to be like hard in terms of resources and time that you have to spend to do. So if we can either find processes that are, I mean, Sebastian told us in the meeting that we have with him that he chose those very, very tiny training, post-training things just because you cannot pre-train a whole GPT on Common Crawl because you cannot do that with a normal computer. So he had to balance and chose examples that we could do. So I'm interested in whatever we can do. We saw already I believe that it was Taha, a presentation about fine-tuning Llama for function calling, which was pretty interesting. So whatever someone can tell us about those processes, I think it would be pretty interesting.
Yep.
Yeah, and we also had Michael's explanations on DPO, that is like reinforcement learning with human feedback related. But yeah, now that you mentioned, both of you mentioned, it would be nice if we can maybe in the middle of book sessions, for example, next chapters are about evaluating methodologies, right? I'll try to see if I can find someone in the internet that like I've seen many people on the internet that talks about evaluation. Um, I'll see. I'll do my best. I'll invite them to join. Maybe not next session, but in a couple of weeks, and see if we have like one session where we discuss about the chapter topics, but with someone that spends 8 hours a day doing that. Maybe it might be fun, right? Could be fun. So yeah, I'll look around and invite people and see if they respond. But yeah, great session. Thanks, Carlos. The other thing that I wanted to mention before we go is next chapter. Is there anybody wants to take the lead on chapter 3, that is evaluation methodology? Remember that you don't need to be an expert on it to lead the chapter. As Carlos and Mashet.
I'm willing to help on chapter 3 if you want.
Yeah, nice, Patrick. Very cool. Yeah. Then, Patrick, I might reach out to you during the week.
Yeah, with the help
in
of
case
the
you need
slides.
anything.
Yeah.
Yeah, in case you need anything. Awesome. Awesome.
Okay.
Thanks. Yeah. Any other questions before we go? Any comments? No. Then thank you all for joining. Hope you enjoy the rest of your Sunday. See you.
Thanks, everyone. Take care. Bye.
Bye.
Yeah, thank you. Bye.